Red light? Yes. Okay. So, a theta's average deviation, i.e. just ignoring the direction nobody uses. And there's very, very good reasons as to why, which we'll explore more in Math 244 quite a bit. Anybody taking calculus in here? A couple of you. Not enough to use that as a formal argument. So we're going to stop talking about that right now. So basically, nobody does it that way for various good reasons, some of which we'll see in 244, some of which you can just trust me, nobody does it that way. So we have to use Tabitha's plus and minus. So in other words, we have to treat this 79 as 2 down and this 83 as 2 up. We have to keep track of that. So essentially what you have then is, you've got 79 is 2 down from 81, 80 is 1 down from 81, 81 is right at 81, and 82 is 1 up, 83 is 2 up. What would Bert's deviations be from his average, which is also 81? Pick one, Lucas.
There's 20.
So you got 20,
61,
you got a 61, so you've got negative 20, if you will, or 21 now.
Yeah.
Love it. Go ahead. 60, what's it, 68?
Yeah, so that's 10, 13.
That's 13, right? So 13 left or 13 down, negative 13. 82 would be
1 off.
Would be 1 up, exactly 1 off. What's that up there? 94, which would be 13 up, right? 13 up. And his 100 would be, I guess, 19 up. Good, good. What should we do with those numbers? So now we've got, if you will, individual variation from individual averages of those data sets. What do you think? Okay, so this might be getting a little bit much to keep track of in our heads. So let's take a step back. Let's look just Ernie. Just Ernie. Let's go back to Ernie. I'm going to put the camera over here for a second. We'll come back to Bert. We'll come back to Bert, I promise. Let's look just at Ernie for right now. Okay. So rather than trying to do this all in our heads, let's keep a little chart together. So I'm going to start by putting X, which is going to stand for the data, which in this case are the exam scores. Exam scores. Okay, so his exam scores, again, are 79, 80, 81, 82, and 83. And order is irrelevant. Order is irrelevant. It doesn't matter what order you put them in, because we're not comparing exam 1 Ernie to exam 1 Bert, or exam 3 Ernie to exam 4 Bert, or anything like that. We're just looking at their 5 exam scores. Cool. So what you guys essentially, I'm going to use a little bit of math symbolism here, because I think the symbols, not symbolism, that makes it sound kind of mystical. Math symbols. I'm going to use some notation, because it'll clean up our argument. What you guys just did was you took each exam score, X, and you subtracted off the average from each one. And that's how we ended up with those negatives and positives. So 79 was his exam score, less the 81, which is the actual average, and that ended up being negative 2. And that means he was, that exam was 2 points below the average, or the 81. And then we did that for all of them. 80 is 1 left, or negative 1 from average, 1 down from average. 81's right there, so it's 0. 82's 1 up, so it's plus 1. 83's up 2, so it's plus 2. So what these are called are the, I don't know what they're called actually. We're going to make up a name for them. They're the individual deviations of the data point. I don't know what they're actually called. We'll make up, that's a good name for them. So what should we do with those? Think what Athena told us to do earlier. Because at heart, what do you think? Cody, right?
That's close. Yeah, chop.
Cody's close, or
Yeah.
Chop's close?
No, chop is what I do, and Cody is close.
Is close enough?
Close
Am I guessing the right
That's
name?
average, yeah.
What's your actual name, damn it?
It's Corey.
Corey! It's not close enough. He's not even close to ours. Is there a Cody in here? Why'd I call him Cody? Damn it. Corey! Corey! Oh, so you're saying chop, chop. So, okay, so chop the negative 2 and the positive 2. Love it. Then we got negative 1, 0, and 1. So, say it again.
Uh-oh, it's 0.
Uh-oh, it's 0. Come back to that for a second. Let's look at Bert's. Corey's onto something here. Remember Bert's deviations that Lucas gave us? His 61 was negative 20. His 65, what is that, 68?
Yeah.
That was negative 13, right? Plus 1 for 82. 94 was up 13, if the math is right on that one, I think. And then 100 is up 19. Now, Corey, I want to make one small adjustment to your argument, which I love, by the way. Rather than lopping top and bottom, I want to stick with the definition of average. So, but if I average these data values, I still get 0. I still get 0 because all the positives cancel the negatives.
Well, that's why that's the line.
Why? Tell me, Lucas.
Because, well, that just makes sense.
What is the line? Remember,
The
go.
line is the average. Of
And the
all
average,
your
what we think
scores.
of?
It's just this, I don't know, the center of it. It's hard to explain.
Which center?
It's the same from the left and the right. It's balanced out. And
That's
so
what I was looking for.
Yeah.
It's the balance point. Friends, if you average these numbers, what do you get?
0.
You get 0. All the pluses and the negatives cancel each other. Negative 20, positive 20, gone. Negative 13, positive 13, gone. Which means, if we look at either Bert or Ernie's data set strictly as deviation from average and nothing else, they're going to cancel. As a matter of fact, for any data set, this sum of this column will always be 0. It doesn't matter what your data set is and whatever values it has in it, how big it is, how small it is. If you add up this column right here, it will always sum to 0. As a matter of fact, in your next homework assignment, the last question is an extra credit. Prove why. Prove why for any data set that always happens. Now, Lucas just proved it in words. Because it has to. That's what the average is. The average allows you to place your finger on a balance point so that the scale balances. What that essentially means is you're taking the extreme value over here, donating some of the value of that to the values over here, which brings that one in and brings this one in, and brings this one in and brings this one in, and essentially you've got 5 data points all stacked on top of 81, which has the same point spread as they are right now. Perfect. Perfect. That doesn't help us in calculating variation, though. It actually makes it harder. Because now everything cancels, and it's like, oh, so now Bert and Ernie are the same again. Because they both sum to 0. Except you can't say that, because obviously there's a difference. So Athena had one solution for us. And I don't mean to disrespect, but nobody uses that, unfortunately, the average deviation. It's in Excel still. It still exists in Excel. But nobody actually uses the average deviation for good reasons, So here's the workaround that statisticians have come up with. What they've done is they've taken the values that are in this column and squared them to take care of the negative values. Hold tight on this one. I have this YouTube channel for COCC Math. That's where all the videos go uploaded to whenever I upload videos. I also have other videos uploaded that explain other concepts. And a student asked me once from, I forget where they were, I think they were in France, why do you square this to get rid of the negatives? Why not just take the absolute value? And the answer is, due to calculus, you can't have a hard point on a graph. This takes care of the hard point. Something squared, x squared. Think about the graph of x squared from algebra classes. It's got a smooth bottom. An absolute value curve has a sharp bottom. You can't have those in calculus and do something called differentiate the actual functions. So this takes care of that, makes a smooth bottom. So let's square the average differences. Negative 2 squared gives you 4. Negative 1 squared gives you 1, 0, 1, 4. Yay! Can we add those? Oh, excuse me. Stupid question. We can add anything. Can we add those and get something non-zero? Yes. So let's add them. This is sometimes called the sum of squared deviations. Some of you guys have taken psychology classes before. Some of you may have seen something in the journals, SS, sum of squares. That's what they're talking about, the sum of the squared deviations. Okay? I don't like stopping right there personally, because the problem with that is, let's look this up a second. The problem with stopping right there, okay, that's gonna break. I'm a little gun shy. Did I tell you, I walked into class a couple days ago and there was a screen laying on the ground, ripped out of the wall. And apparently it hit the instructor that was in there, the class before me. She had pulled it down, the whole thing just came ripping out of the wall. So I'm a little gun shy now with these 150-pound screens kind of hanging up there. So. Oh, really? Yes. Yeah, those look a little burly, the things that are hanging up there on the wall. Plus there's 4 of them. This one had 2. And it look like plant holders holding it up. We're okay now. Terrifying. Anyway, exam score, points. Deviation from exam score in points. Here's a problem I don't like. You took points and squared them. You now have square points. That doesn't make a whole lot of sense. It doesn't make a whole lot of sense, because what is a squared point? It's really nothing. It doesn't have any meaning. We'll deal with that. We're going to deal with that by taking the square root of it eventually, but not quite yet. I want to analyze this. Now, this is a definition. I have no other better way of doing this other than just launching into what it actually is, and I'm actually too far to the side. Let me put this back. I'm trying to make this useful for you guys for later. There's a measure of variation that's called the sample variance. Sample variance. It's defined to be the sum of those squared deviations that you just calculated. But the idea of it is you want to talk about an average variation. So logically, you'd think you would take that sum of all of the squared variations and divide it by what? If you had to guess to divide by which number to make it an average measure of variation, what would you divide by? 5. Logically, you'd think 5. Algebraically, you can't. You have to divide by 1 less. Now, there is a very, very great algebraic reason as to why it's n minus 1 and not n. If you're interested, I steer you to the enrichment page of the website, where I kind of line it out for you. It takes a little while to justify. There's a very, very good algebraic reason. I've tried it in class. It backfires. It's a terrible thing to do in class. Put you all to sleep. If not, it makes you sick, nauseous, that thing, knee joint inflammation. So it has to be n minus 1 algebraically to become something called an unbiased estimator. Don't worry. You'll never have to memorize that or regurgitate it, except right now we're going to use it to actually calculate this for our data points. So the sum of that bad boy is 10, divided by n minus 1, which in this case is 4, because we have 5, less 1 is 4. And that ends up being 2.5. Yay, us, 2.5. 2.5 what? 2.5 what's? What does that mean, 2.5? Exactly, right? We got a chuckle. We're like, yeah, I don't know anymore. Because we knew what the 81 average was. He has an average of 81, right? 81 what? Points on an exam, correct? Points on an exam. So 81 points on an exam is his balance point. What's 2.5? That's plus or minus square points. But wait a minute, that's like trying to add feet to gallons. Like you can write, 1 foot plus or minus 2 gallons, but it means absolutely nothing. You need to have the same unit. So this all goes back to Tabitha, what you were talking about before. It all goes back to don't frown. It's a good thing. When you mention variation from the average, there's one measure, and one measure that is the predominantly most popular, most often used measure of variation, and it's called the sample standard deviation. This is the big guy. This is the one that gets used over and over and over again in research, in journals, in publications, what you're going to be talking about on average in your study. It's not to use average in a very, very colloquial way. And all the sample standard deviation is computationally. It's called S. It's got the name S, which is very, very nice just for the sample standard deviation. It's lovely, lovely. Computationally, it's just the square root of the sample variance. Why does this make me happy? Because it gets rid of what? Say that again, Tammy. It's not square points anymore. If you have square points and take the square root of square points, all you have is left is what? Points. You have a common unit then. So for our particular case, for Ernie, that sample standard deviation is a square root of 2.5 square points. That's a 2.5. And what is this? Is that like 1.5? 1.58. 1.58. I'm going to go ahead and call that 1.6 if you don't mind, just to give it one decimal. Somebody asked me a great question last class. How many decimal places should you have in the result of a computation? Who's taking chemistry in here? Chemistry? Field that question. Tell me your name again too, my friend. David, how many decimal places should you have? I'll put you on the spot. You can feel free to tell me to get that out.
It depends on how many significant figures.
Exactly. It depends on significant figures. Basically, you can't have any more precision than your least precise measurement. So since our least precise measurement was whole number, technically that should be rounded to 2, because that's the same number of sig figs, if you will. don't worry about that kind of stuff, because if only one person's ever studied sig figs, I can't expect the rest of you to have that.
Well, they drilled it into.
I know they did, and it's important, because you're talking about very precise measurements in chem. This is much more seat of your pants kind of approximations. There's good math behind it, obviously, but a lot of how the numbers were gotten, the precision is unknown. So I'll just tell you what's around you. I'll just tell you. I tend to not put more than one decimal place above what we already had in the raw data, just on habit. But don't sweat that kind of stuff. I don't want you to.
So you'll say around the nearest 10.
Nearest tenth, nearest hundredth, something along those lines, David, absolutely. So, more important than how much precision in our result, I want to know what that means. I want to know what that means. Let's go over here, and I'm going to take away raw data. I can get rid of these, because you already have them in your notes. I want to know, that is like the worst eraser ever.
Yeah.
It's okay though. Getting better. What does it mean? What does it mean? Ernie now has a sample standard deviation of 1.6. 1.6 what? Points. Use it in a sentence. You're out there, you're working on your rose bush, your neighbor comes out and he's going, Sean, Tammy, Corey, David, whoever, Tabitha, the standard deviation thing, I read it in this research journal, I'll take it from my master's classes. What the hell does it mean? This guy Ernie, he's got a 1.6, and his average is an 81. What the hell, how do you put the 1.6 together with the 81? You're out there trimming your rose bushes, what does it mean, Tammy?
It means that really it could be 1.6 points in either direction of his average.
That's exactly what it means. The best way I found to think about what standard deviation means, so if you can imagine an arrow coming up to it like this. This is probably the most concise way. Tammy just said it verbally perfectly. It's on average, how far each data point is from X bar. That's essentially what the sample standard deviation is measuring. It's on average how far away the data points are from average. It doesn't tell you what direction. It just tells you the distance, how far away they are. This is why, at heart, it ties into what Athena said earlier about taking the absolute value. It's essentially the same argument. It's how far away they are. So Ernie, on average, is 1.6 points away from his average, and you can see that in his graph. This one's 0, these are each 1, these are each 2. So by that computation, it's about 1.6. Now technically, if you do it numerically algebraically, it's 1.2 by absolute value. But that is not the computation that's used for very good reasons. And there's very, very good, I feel like almost like a fraud saying for very good reasons. The very good reasons are calculus. But nonetheless, that's what that 1.6 interpretation is. Just as Tammy said, on average, it's how far away from the mean, X bar, the data points are on average. So that's Ernie's. What do you think Bert's is?
Much bigger.
Much bigger. Gotcha. Much bigger. How much bigger? Now, take a pause. Take a pause. Stop right there. You're never going to do these again by hand. It's silly. It becomes ridiculous to do this stuff by hand over and over and over again. The point of doing it by hand once is to understand, number one, why this happens. If you don't do it by hand once, you miss this. And although Lucas explained it perfectly with respect to the average, that might not be clear, that because the average is a balance point, this will always sum to 0. Then we have to deal with how to fix that. So we dealt with it, fixing it this way. I know that was a little bit lectury, and I apologize that. This is the way statisticians do it. They square. I love the absolute value idea from Athena. So this is why you do it once by hand. You never do it by hand again because I want you guys playing with data sets that have hundreds, if not thousands, of things in them. And I don't want you doing hundreds, if not thousands, of rows of exactly. Shelby's like, I don't want to do that either. No, understandable. It's ridiculous. It becomes ridiculous. The takeaway, though, is no matter what size our data set, this means the same thing. On average, how far apart a data set is from the average of that data set. That's the takeaway, friends. That's all it always is. Now that you know that, and I won't let you get off easy, you'll be saying that all the time. You'll talk a lot here when you communicate with me. I won't let you get off with, the answer's 5. 5 what? What does it mean? You'll constantly be saying that in this class. But to save us the agony, to save us the agony of having to compute this stuff manually, grab your machines, grab your TIs. Let's start getting into there and showing how to use those. Because that's going to get us the results in a much more efficient way. And I've gone ahead and installed this on the computer up here. There we go. Make sure I can see this okay on the camera, because this will help us out later on. If you guys, let's do this. If you guys want to refer back, we'll see the button pushes and the results. Okay. So we're going to fire up the machines. Go ahead and turn them on. Now, I know you guys have used these quite a bit in previous math classes. Chances are you probably didn't use the stat functions all that much. I'm sure you use them a little bit. I know you guys in 105 I had you use them a little bit. Of course. But I mean, depending on who you had Math 111 with or 95 with, you may have never turned them on before. So what you're looking at right now, FYI, this is the built-in that you can install on the machine from the link off the materials page. It looks just like this. So you basically, you push the buttons with the mouse like you push with your finger. The only downside to this is I've written some programs for the actual machine that we'll be using eventually in this class, and I don't know how to put those into this. So that's the only downside. Okay, so anyway, we're on. Press the stat button. Press the stat button. There are 3 sub-menus off of this stat button. Edit, calc, and tests. Tests we're not going to use in this class at all. That's the realm of 244. That's all we use in 244 is the tests menu. We're going to use edit and calc. And edit in particular is the one that we're going to play with a lot today. Well, both edit and calc. So go ahead and select one for edit. And what I want you to practice doing right now is getting data in. So if you would, get Ernie's data into L1 and get Bert's data into L2. So when I say get data in, just type in Ernie's test scores. So 79, then press enter. 80, press enter.
What if I already have numbers in my...
Oh, who has numbers in their lists? A couple of you. If you have numbers in your list, you can just overwrite them. But if you have more than 5, the best thing to do is to clear them. To clear a list, thank you for asking that, Lucas. To clear your list, if you have to clear them, just arrow up until you're on top of the list.
Hit clear, not
Hit, yes ma'am, hit clear,
not delete.
and then down. Well, you can hit delete, and then you have to go put it back in, which is kind of a pain in the ass, but yeah. So anyway, yes, so you basically, if you have numbers in, arrow up, press clear, press enter, and it'll take care of whatever you've got in. Or, if you only have a couple numbers, you can just overwrite them. But chances are you have more than 5. Thank you, Lucas, very good question. Beth, go.
I'm missing L2 again.
No problem. If anybody's missing list, this does happen. Athena mentioned if you press delete as opposed to clear, it'll just like, for example, if I'm up there and I'm on L, like, so I can go over to L2 and press delete. Oh crap, now L2's gone. Everybody do this right now. This doesn't hurt anybody. Press stat. This doesn't hurt anybody's calculator. Press stat. Press 5 for set up editor, and then press enter. If you already had all your lists, they're still there. If you didn't, the ones you didn't have are now back. It's a bug. These things are loaded with little bugs that they never fixed. That's the beauty of being a monopoly. You don't have to fix anything. We keep buying their stuff. So, cool. Ben's back. Bueno. Now, you can also use the other lists. I just told you to put Bert and Ernie in L1 and L2. So you can use all the lists you want. So, but let's just, for the time being, let's just put Bert in L2 and Ernie in L1. Oops, not 80 point. So enter each time will get you from line to line. And then the arrow buttons over here take you over to L2. Then you can enter Bert's. He had 100, he had 61, 82. What else do you have? 95?
94.
94, thank you. And 60. So was that one 60?
Sorry, 68.
68? Okay, awesome. And there they are. So you got Bert, L1, Ernie, L2. You can also name lists, like you can go far off to the right and name like Ernie and Bert. I don't think it's worth the trouble. I mean, it's just keep track. Ernie's in L1, Bert's in L2. Use your, or write it down like I would do. So, what we're going to do first is we're going to calculate all the wonderful stuff that we did for Ernie in a half a second. So press your stat button again. All these other choices are fantastic, except they're not used all that often. Sort A and Sort D, we'll deal with those in time. We don't need them right now, we'll deal with those in time. Clear list is another way of getting lists cleared out. You put clear list, the list name, and then it wipes it. And setup editor, you saw what that just did. I want to go over to calc right now, which is calculate. Lots of stuff in this menu, tons of stuff. Only one we are going to use in this class. Only one, and it's the very first one var stats. One stands for single, var stands for variable, and stats stands for statistics. What variable are we measuring right now in this problem? What are we trying to, what are we interested in for Ernie? His, well, of his what? You got it, Chessa, of his what? Of his scores on his tests. That's the variable we're measuring, his scores on his tests. We're going to get a whole bunch of stuff. We're going to get his average, we're going to get his sample standard deviation, we're going to get his median, we're going to get a bunch of other stuff you don't even know what it is yet. But the variable we're interested in measuring is his exam score performance. That's why it's a one var stat. It might seem like it should be two vars because it's Bert and Ernie, but we're only doing each one individually. So we're doing Ernie first, then we'll do one var stats on Bert. We're not comparing Bert